So we will continue the discussion of second law of thermodynamics. In last session we have seen the various terms associated with second law of thermodynamics such as thermal energy reservoir, thermal efficiency, heat engines. Today we will be focusing on what is a heat pump and what is a refrigerator, what is the difference between these two. Please recollect the Clausius statement of second law of thermodynamics, where we have seen that the transferring of thermal energy from a low temperature reservoir to high temperature reservoir is impossible for any machine operating in a cycle without the help of an external aid. Some external work input is required to transfer heat from low temperature to high temperature reservoir. So such device which transfers heat from low temperature to high temperature with the help of some external aid is termed as a refrigerator or a heat pump. So coming to the exact understanding or definition of heat pump and refrigerator, heat pump is a thermodynamic system. It is a thermodynamic system operating in a thermodynamic cycle that removes heat from a low temperature body and delivers heat to a high temperature body. Refrigerator is also the same device. The difference between the heat pump and a refrigerator is the desired result. The desired result in the case of a heat pump is the amount of heat rejected to the high temperature medium. In the case of refrigerator, the desired result is the amount of heat that can absorb from the low temperature medium. So here you can see in the schematic, you can see the refrigerator. This is a refrigerator. Okay. So this is a cold refrigerated space. So this is a violation of Clausius statement. Obviously, this schematic represents the violation of Clausius statement, but actually there should be some network input. So here this QL 5 kilojoules of energy is absorbed from the cold refrigerated space. So that is the desired result in the case of a refrigerator. But if it was a heat pump, the desired result would have been this QH, the amount of heat that is rejected on the warm environment. Now coming to the terminologies associated with this refrigerator and heat pump, instead of thermal efficiency, here the term used is coefficient of performance. Why? You know that any work producing device could be compared with the thermal efficiencies, or the performance index of a work producing device such as heat engine could be well understood or analyzed using thermal efficiency. Net work output divided by the ratio of net work output and heat input, right? Out of the total heat given to the engine, how much is usefully converted to work. So that is the thermal efficiency. But here in the case of a refrigerator or a heat pump, only transfer of thermal energy from low temperature reservoir to high temperature reservoir is taking place. So there is no work output. Rather, there is a work input, isn't it? So index of performance of any refrigerator or heat pump is expressed in terms of COP, or coefficient of performance. In shortly it is written as COP. The ratio of desired result to the input, required input. Desired result to the required input. So this measure of performance, the obvious difference from the thermal efficiency is this could be greater than 1. Whereas the thermal efficiency is always less than 1. But COP on the other hand could be greater than 1. And we want the COP to be as large as possible. In the case of a refrigerator, we want the refrigerator to absorb as much heat as possible from the cold refrigerator space, or in the case of a heat pump, we need as much heat to be rejected to the high temperature reservoir as possible. So for heat pump acting like a refrigerator or an air conditioner, the primary function will be the transfer of heat from the low temperature system. So the QH is the desired result in the case of heat pump, and QL is the desired output or result in the case of a refrigerator. So for COP of a refrigerator, coefficient of performance of a refrigerator is QL by W net in. In both the cases, whether this system is refrigerator or HP heat pump, the net work output is W net in, but the desired result is different. In the case of desired result of a refrigerator is QL, and that for a heat pump is QH. Now, in order to understand the relation of COP between refrigerator and heat pump, we are applying the first law of thermodynamics to the cyclic refrigerator, that is the net heat transfer is equal to net work transfer. So QL minus QH minus, there is no work output is 0, minus W in is equal to change in internal energy. For a cyclic process it is 0. So W in is equal to QH minus QL. The net work in to the system, refrigerator or heat pump is a work absorbing device, work consuming device. So which is equal to QH minus QL. The coefficient of performance becomes, for a refrigerator, it is QL minus QL divided by QH minus QL. QL divided by QH minus QL, where QH minus QL is the work input. So when the device is acting as a heat pump, the numerator will be QH. So COP will be QH by QH minus QL. So under the same operating conditions, you can establish the relation of COP of heat pump and a COP of refrigerator through this. COP of a heat pump is always greater than COP of a refrigerator by unity. So that's all for today's session. So please refresh the concepts by solving simple problems from any textbooks of thermodynamics using these concepts, especially steady flow energy equation, the thermal efficiency. One example was shown in the previous session, and the heat pump and refrigerator. Thank you for watching. Have a good day.